Hello everybody, my name is Iman. Welcome back to my YouTube channel. Today we're continuing our lecture on stoichiometry and we left off at objective 6 titled chemical equations. Now chemistry attempts to understand many of the changes that we encounter around us. Some of the changes that we can encounter can be classified as physical changes and some can be classified as chemical changes. A substance that undergoes physical change maintains its chemical composition. For example, when an ice cube melts and forms liquid water, which then evaporates, two different physical changes have occurred: melting and vaporization. Since the composition of water is H2O, whether it's in the solid phase, the liquid phase, or the gas phase, these are examples of physical change. Now, when a substance undergoes a chemical change, its atoms rearrange to form different substances. And things that indicate a chemical change has occurred include color changes, bubble formation, or odor and temperature change. For example, when we have solid magnesium metal that's placed in a solution of hydrochloric acid, the solid magnesium dissolves and hydrogen gas bubbles out of the solution. This is an example of a chemical change. This chemical reaction can be represented using a chemical equation. That's what we have written here, right? Mg plus 2HCl gives us MgCl2 plus H2. Now, the substances on the left side of the arrow are the reactants, and those on the right side are the products. Also notice that a one-way arrow is being used to describe this reaction, and one-way arrows are used to describe reactions that proceed in one direction, where the substances on the left side, the reactants, react to form those on the right side, the products. In later chapters, we're going to encounter the equilibrium arrow that's used for reversible reactions, but we're not going to worry ourselves about that right now. Now, an important law to consider in regards to both physical and chemical reactions is the law of conservation of mass. This law states that there is no detectable change in mass during the course of any chemical reaction. Atoms are neither created or destroyed. They simply rearrange to form new substances. And because of this, chemical equations must be balanced to assure that the atoms and the quantity of each in the reactants matches up the atoms and the quantity of each in the products. So if you look at this example, you'll notice that there is one magnesium atom in the reactants and one magnesium atom in the products. There's two hydrogen atoms in the reactants, two hydrogen atoms in the product. All right, and so on and so forth. Now you might be asking, well, how do we balance chemical equations? This is done by placing coefficients in front of the formulas to indicate the relative amount of reactants and products. And then the follow-up to that follow-up is, what are the steps to balancing a chemical equation? And that leads us into objective 7. Now I'm going to go over the rules for writing and balancing chemical equations, and then we're just going to jump right into some practice problems. The first two rules are for problems where you're not even given a chemical equation. You might be given a word problem where you have to determine how to write the chemical equation for it anyways. The first step in that case is, what reaction is occurring? What we have to figure out the reactants, the products, and the physical states of those reactants and products. And then step 2 is then to go ahead and write the unbalanced equation that summarizes the reaction described in step 1. So that step 1 and step 2 are for cases where you are not given a chemical equation. If you are given a chemical equation, then you want to start with step 3. Step 3 says balance one atom at a time, starting with the substance that has the most elements present. Save the simplest substances, such as uncombined elements, for last. If necessary in this first step, you can use a fractional coefficient to balance the simplest substance. Step 2, though, says, remember, we usually prefer to use the smallest whole number coefficients. So if there are any fractional coefficients that you used in step 1, now is the time to multiply each coefficient by a factor that will result in the smallest whole number coefficient. And then last but not least, in step 5, you want to check each atom to ensure that the equation is balanced. All right, with that, let's go ahead and just jump into some problems. This first problem says, balance the following chemical equation. Nice, we're given the equation itself. So we can actually skip step 1 and 2 and just hop right in step 3, where we want to balance one atom at a time, starting with the substance that has the most elements present. The substances with the most elements present are iron oxide and carbon dioxide. All right, so we're going to start with these. The first atom that we should balance is going to be oxygen. And the reason for that is because both carbon and iron exist as their own elements in this chemical equation, so they're going to be easier to balance later on. So we're going to want to start with oxygen. Okay, let's divide this reaction by half, and let's look at oxygen on the reactant side. On the reactant side, we have 3 oxygens. On the product side, we have 2 oxygens. Okay, so if we want to balance this, what's a multiple? What's the smallest multiple in common between these two for 3 oxygens on one side and 2 on the other? Well, 6. We can add a 2 in front of iron oxide here, and that's going to give us a total of 6 oxygens on the reactant side. And then we could add a coefficient of 3 in front of carbon dioxide to get 6 oxygens on the product side, and now the oxygens are balanced. Okay, oxygen is balanced. We can move on to other elements. Let's move on to iron. All right. For the reactant side, we have 4 iron atoms. Okay, 2 of iron oxide, and iron oxide has 2 irons, so 2 times 2 for a total of 4 irons. On the product side, we only have 1 iron. So to balance it, we can add a coefficient of 4 in front of this iron, and now on both sides, there are 4 iron atoms. So those are balanced. Wonderful. Now we can move on to carbon. On the reactant side, we have 1 carbon. On the product side, we have 3 carbons. To balance this out, we're going to add a coefficient of 3 in front of this carbon on the reactant side. And now we have 3 carbons on both sides. Okay, so we've completed our first step. We balanced 1 atom at a time, starting with the substance that has the most elements present. Step 2 tells us to adjust the coefficients to remove any fractional coefficients. There are no fractional coefficients that we had to use here, so no adjustment is necessary. And then the last step is to check each atom to ensure that the equation is balanced. Again, we have 4 iron on the reactant side, and on the product side, check. We have 6 oxygens on the reactant side, 6 oxygens on the product side, check. And 3 carbons on the reactant side and 3 carbons on the product side, check. This verifies that all the atoms are balanced. So this equation is correct. We have 2 iron oxide plus 3 solid carbon gives us 4 iron plus 3 carbon dioxides. Wonderful. Let's go ahead and do another example problem. This is a word problem, so we're going to have to do step 1 and 2 here to write a chemical equation. So this says at 100 degrees Celsius, ammonia gas, NH3, reacts with oxygen gas to form gaseous nitric oxide, NO, and water vapor. This reaction is the first step in the commercial production of nitric acid. Balance the equation for this reaction. Okay, so the first step is to identify our reactants and products and the states that they're in. So for our reactants, we have ammonia gas and we have oxygen gas, and they react to form the products gaseous nitric oxide and water vapor. So we know our reactants and products and their states, so we can go ahead and attempt to write the chemical equation. We have NH3 gas plus O2 gas. That gives us NO gas plus H2O gas. Awesome. So we've completed steps 1 and 2. Now we can move on to step 3, where we want to balance 1 atom at a time, starting with the substance that has the most elements present. Now, since we see that oxygen is an element by itself on the reactant side, we're going to actually begin with NH3 instead. All right, so we're going to start off with NH3, and we're going to work with the hydrogen atom first. Okay, so on the reactant side, we have 3 hydrogens. On the product side, we have 2 hydrogens. So we're trying to find a common multiple here, the smallest common multiple, and see what coefficients we can add in front of these two to make them equal. 6 is a common multiple, so we can add a 2 right here, and that gives us 6 hydrogens. And we can add a 3 right here, which also gives us 6 hydrogens. So the hydrogens are now balanced. Wonderful. Now let's do nitrogen next. On the reactant side, we have 2 nitrogens. On the product side, we have 1 nitrogen. So if we add a coefficient of 2 right here, now the nitrogens are balanced. So far, so good. Now we have oxygen left. On the reactant side, we have 2 oxygens. On the product side, we have 2 oxygens over here and 3 oxygens over here for a total of 5 oxygens on the product side. Okay. Now, if we have 5 oxygens on the right side of the arrow, in order to have 5 oxygen atoms on the left side, we're going to have to multiply this by a fractional coefficient, 5 over 2. If we multiply this by 5 over 2, now we have 5 oxygens on the reactant side, 5 oxygens on the product side. They're balanced. Okay, now we can move into step 4, which says now we have to adjust the coefficients to remove any fractional coefficients. And here in this example, we've used fractional coefficients that we have to get rid of in this step. So how are we going to do this? We only have one fractional coefficient. It's 5 over 2. In order to remove the fractional coefficient 5 over 2, we have to multiply the whole chemical equation by 2. All right, we have to multiply all of it by 2. And this means that we now have 4 ammonia, we have 5 oxygen, we have 4 NO, and we have 6 H2O. All right, and now we've gotten rid of our fractional coefficient. And it leads us to our last step, where now we have to check if everything is actually balanced. So let's recount our atoms. On the reactant side, we have 4 nitrogens. On the product side, we also have 4 nitrogens. Check and check. On the reactant side, we have 12 hydrogens. On the product side, we also have 12 hydrogens. Check and check. All right, for oxygen, on the reactant side, we have 10. And on the product side, we have 4 over here and 6 over here for a total of 10 as well. So everything is balanced. This equation is correct. Wonderful. So we did it. Now, one more thing I want to talk about here is combustion reactions. This is a type of reaction, and combustion reaction is a term that's used to describe reactions where something burns in oxygen gas. And it is going to be characterized by the release of heat and the presence of a flame. Now, you're going to see in this chapter combustion reactions of hydrocarbons specifically. Hydrocarbons are molecules that only contain carbon and hydrogen. And when a hydrocarbon undergoes complete combustion in O2, the products are carbon dioxide and water. And so now what we want to do is balance combustion reactions. We follow the same protocol. I just want us to get familiar with this kind of reaction because it will appear later down the line in our general chemistry course. What we have here is C4H10 or butane reacting with oxygen gas to give us carbon dioxide and water. And since we already have the chemical equation written, we can skip step 1 and 2 and just hop into step 3 where we balance one atom at a time. Now the simplest substance is O2, which is an element. We're going to save it for last. So what we're going to focus on balancing first is actually carbon. Carbon here in the reactant side there's 4 carbons, and on the product side, there's only 1 carbon. So to balance this out, we're going to add a coefficient of 4 right in front of CO2 so that the carbons on the reactant and product side are now balanced. Next, we can do hydrogen. On the reactant side, we have 10 hydrogen atoms. On the product side, we only have 2. To balance it, we can add a coefficient of 5 right here so that we have 10 hydrogen atoms on both the reactant and product side. And then last but not least, we have oxygen. On the reactant side, we have 2 oxygens. And on the product side, we have 8 plus 5. So we have 13 oxygen atoms on the product side. Now, to balance the number of oxygen atoms on the reactant side, we're going to have to use a fractional coefficient of 13 over 2 so that we have 13 oxygen atoms on both the reactants and product side. Now, the next step after this is obviously to get rid of our fractional coefficient. And to do this, we have to multiply our whole chemical equation by 2. And so what does this give us? I'm going to erase some of this work that we have here so that we can write this equation with our new coefficients and then do our last step where we make sure that it is truly balanced. So if we're multiplying by 2 throughout, we have 2 butane molecules, 13 oxygen molecules, 8 carbon dioxides, and 10 water. And our last step is to triple check that indeed these coefficients now lead to a balanced chemical equation. On the reactant side, we now have 8 carbons. On the product side, we also have 8 carbons. Check and check. For hydrogen, we have 20 on the reactant side, and we have 20 on the product side. Check and check. And then for oxygen, we have 13 on the reactant side, and on the product side, we have, sorry, not 13, this should be 26 if we multiplied it by 2. No, it should be 13. I'm so sorry. 13 times O2, which is 26. Ignore my poor math skills right now. All right, we have 26 oxygens on the left side, and we have 16 plus 10 oxygens on the product side for a total of 26. Check and check. So with that, we went ahead and we balanced this equation. Wonderful. And that allows us to move into our next objective titled Stoichiometric calculations. So far in our lecture, we've talked about moles quite a lot. And we know a couple of important points about moles so far. One, mole is a number word, so it can be used as a conversion factor in dimensional analysis and stoichiometry. And 2, mole relates to mass. 1 mole of an element has a mass equal to the atomic weight of that element expressed in grams. Now, in this section, we want to add another important point about moles, and that is the mole concept provides mole-to-mole ratios. This allows us to determine quantitative relationships between reactants and products in chemical reactions. And there are 2 places to get mole-to-mole ratios. One is the subscripts of chemical formulas, and the other is coefficients of balanced equations. Now, we're going to see how this idea of mole-to-mole ratios can be useful for solving different kinds of chemistry-based problems. We're going to specifically see it in the next objective when we talk about limiting and excess reagents. But with that being said, I want to kind of work you through the strategy for attempting these kinds of problems, and then we're just going to do some examples together. So earlier in the lecture, we talked about how we can convert from number of particles to moles, from moles to mass, or any kind of combination of these. And we saw that we are using a strategy where we align our units in a way where our unwanted units cancel out, and we end up with an answer that has our desired units. And we've learned 3 important conversion factors so far. One is Avogadro's number. 1 mole equals 6.022 times 10 to the 23 atoms. Another is molar mass, right? 1 mole of an atom of any kind equals its mass in grams. And now we just talked about mole-to-mole ratios that are used to show quantitative relationships between different substances. And we're going to put those into effect in multiple steps to be able to convert from one desired outcome into another. So for example, all right, let's say you have reactant X gets converted to product Y, and you're given, for example, mass of X, and you want to figure out mass of Y. How do we figure it out? The key is knowing these conversion factors that we just discussed: Avogadro's number, molar mass, and mole-to-mole ratios. And so first step is if you're given a chemical equation like X equals Y, if it's not balanced, you want to balance it. Let's pretend it's balanced and it's a 1-to-1, all right? Second step is you want to convert the known mass of the reactant or product to moles of that substance. So if we're given mass of X, the first thing that we want to do is convert it to moles of X. And we can do that using molar mass. The third step is then to use this balanced equation of 1x gives us 1y, all right, to use appropriate mole ratios to then calculate the number of moles of the desired reactant or product. So we went from mass of X to moles of X, and then we can use a mole to mole ratio to go from X to Y. For 1 mole of X, there is 1 mole of Y. And our units will cancel out in a way up to this point that we end up with units of moles of Y. Now, if our goal is to figure out mass of Y, then our last step will be to convert moles of Y back to grams using molar mass. Now, this question can be asked in a variety of ways as well, right? We can maybe be given, for example, number of particles and asked to figure out mass of Y. In that case, the trajectory you want to follow is obviously convert number of particles to moles of X. All right, always to moles, so that you can then use a mole to mole ratio to get to the moles of Y, and then do whatever you need to with moles of Y depending on what the problem asks. Okay, so there can be a variety of combinations that you might be asked for problems where you're going to have to figure out how to cancel unwanted units and reach your desired outcome. And again, the best way to learn this, especially in chemistry with everything, is to do practice problems. So let's go ahead and tackle this first one. How many chloride ions are present in 25 grams of aluminum chloride? First thing we want to do, let's write down what we know, or want to know actually. We want to know number of chloride ions. That's our goal. And what we're given is the mass of aluminum chloride. We know that we have 25 grams of aluminum chloride, AlCl3, right? And we know aluminum has a 3 plus charge, chlorine has a -1, crisscross, we get AlCl3. That's aluminum chloride. Okay, this is what we want to know, number of chloride ions. And what we have to start off with is 25 grams of aluminum chloride. Now we have to think about how we want to apply conversion factors in order to cancel unwanted units. And our 3 important conversion factors in this chapter: Avogadro's number, molar mass, and mole to mole ratios. So keeping that in mind, let's go ahead and write down 25 grams of aluminum chloride. The first thing we want to do is obviously convert this to moles of aluminum chloride, and we can do that using molar mass. The molar mass of aluminum chloride, I'm just going to give it to you, is 133 grams of aluminum chloride for 1 mole of aluminum chloride. And notice how grams cancels out this way. Now, since our goal is to get number of chloride ions, we want to move away from aluminum chloride to just chloride. How do we do this? Well, now we can use a mole to mole ratio to convert from aluminum chloride to just chloride. How do we do this? Well, we said we can get mole to mole ratios from 2 places. We can do it from the coefficients of a balanced equation. We're not dealing with a balanced equation here. Or we can do it from the subscripts of a chemical formula. We have a chemical formula. Aluminum chloride, if we look at this, for 1 aluminum chloride molecule, we have 1 mole of aluminum and 3 moles of chloride. So we're going to use that relationship. We're going to say for 1 mole of aluminum chloride, we have 3 moles of chloride. All right, now we're getting so close. Our goal is number of chloride ions. The last thing we need to do now is use a conversion factor, Avogadro's number. For 1 mole of chloride, we have 6.022 times 10 to the 23 ions of chloride. Wonderful. And notice how everything cancels out except number of chloride ions. So we're going to have our answer, and the unit that's associated with it is chloride ions. If we plug this into a calculator, we should get 3.39 times 10 to the 23 chloride ions. All right, so just to go over this, we started off with 25 grams of aluminum chloride. The first conversion factor we used is molar mass to go from grams to moles of aluminum chloride. That was that first conversion. The second conversion was a mole to mole ratio. We went from 1 mole of aluminum chloride. We know that it contains 3 moles of chloride. And then our last and final conversion is using Avogadro's number to convert from number moles of chloride to number of chloride ions. Wonderful. we did it. Let's go ahead and do another example problem together. Okay, so this one says, how many grams of hydrochloric acid are needed to react completely with 15 grams of aluminum? Okay, so let's do this. What we have here is aluminum plus HCl gives us aluminum chloride and H2. Now, quickly, the first thing we want to do is actually make sure if this is balanced or not. All right, we have one aluminum on both sides. That looks good. We have one chlorine atom, but 3 on the other side. Okay, so this is not balanced. So that's the first thing we're going to do here is make sure we balance this. We're going to divide this in half. All right, we're going to ignore aluminum because it exists as its own element. So we'll leave that for last. And same with H2. So actually, we're going to start by balancing Cl. So on the reactant side, we have 1 Cl. On the product side, we have 3 Cl. Okay, so to balance this, let's put a 3 in front of HCl right now, and that gives us 3 chlorine atoms on both the reactant side and the product side. Okay, so far so good. Let's do hydrogen next. For the reactant side, we have 3 hydrogens. For the product side, we only have 2. Okay, so we have a bit of a problem here. We need to make sure that these are balanced. Well, what's a common multiple between 3 and 2 right here? The lowest common multiple, that would be 6. So let's modify this coefficient to match up with that. And we're going to do 6 here, right? Because 3 times 2 is 6. So now what we have is 3. Oh, actually, we have 3, but now it's a 6, so we have 6 total hydrogens. Okay, sorry about that. And over here, we're going to add a coefficient of 3, so now we have 6 hydrogens on the product side. Okay, one thing that we have to do now is go back to our chlorine, right, because we modified this to make sure that we aligned things properly. Now, on the reactant side, we have 6 chlorines. And on the product side, we have 3. So we need to fix that by adding a coefficient of 2 right here. And now our hydrogens and our chlorines are all lined up. Okay, now we have a last element that we need to make sure is balanced, and that is aluminum. On the reactant side, we have 1. On the product side, we have 2. So we're going to add a coefficient of 2 right here. And now everything is balanced. Okay, and we don't have any fractional coefficients to fix. Everything is good. All right, now that it's balanced, I'm going to erase some of this work, and we're going to actually get to the meat of the problem. Okay, the meat of the problem is, well, how many grams of HCl are needed to react completely with 15 grams of aluminum? So what we're given to start off with is 15 grams of aluminum, and our goal is to get to grams of HCl. Okay, so we're going to start off by writing what we know, 15 grams of aluminum. We're going to go ahead and convert that to moles of aluminum so we can use mole-to-mole ratios to move away from talking about aluminum to talking about HCl. Okay, so here we are going to, let me zoom in since my pen doesn't want to work, 15 grams of aluminum. We're going to use molar mass to convert this to moles. Aluminum, you can look at this at the periodic table, 26.8 grams of aluminum per 1 mole of aluminum. All right, so now grams of aluminum cancel out. We have moles of aluminum. Cool. Now, there's supposed to be a 2 here. It disappeared. I accidentally erased it. Now we can use mole-to-mole ratio to move from aluminum to hydrochloric acid. And here, to do that mole-to-mole ratio, we use our balanced chemical equation. For 2 moles of aluminum, we have 6 moles of hydrochloric acid. So we write that 2 moles. For 2 moles of aluminum, we have 6 moles of HCl. And notice how moles of aluminum cancel, and now we're in units of moles of HCl. Our last step is just to convert this to grams of HCl so we can use molar mass here. For 1 mole of HCl, we have about 36.5 grams of HCl. Moles of HCl cancel, and the units that we're left with for our answer is going to be grams of HCl. If we calculate this using a calculator, we're going to get 60.8 grams HCl. So the answer to how many grams of HCl are needed to react completely with 15 grams of aluminum is 60.8. Wonderful. With that, we can move into our last and final objective on limiting and excess reagents. When chemical reactions are carried out, most of the time, one of the reactants will be completely consumed before the other reactant is. The reactant that is completely consumed in a chemical reaction is called the limiting reagent, and the substance that is not all used up is the excess reagent. Now, what does this look like? Well, let's consider this. Let's say we have two different reactants, reactant A and reactant B, and they give us product AB. The most product produced is going to be limited by the reactant that gets consumed first. An easier way to think about this is obviously with food. Say you have 4 burger buns and 3 hamburger patties. What is the most complete hamburgers you can make? Well, even though we have 4 burger buns, we only have 3 patties. And so the limiting reagent here is the patties. And so the most complete hamburgers we can make is just 3. The excess reagent here is the buns because 1 is left over and there just isn't enough of the patty reagent to make more of the hamburger product. Now, in addition to this idea, another thing that we should cover, and this is especially important if you're taking a general chemistry lab course alongside your lecture, is understanding the difference between theoretical and actual yield. So whenever we use stoichiometry to predict the amount of product that should be obtained, this quantity is the theoretical yield. Theoretically, if everything went well in the reaction, no error in preparation or transfer or anything of the sort, this is how much product we should get. Now, the actual amount that you obtain is called the actual yield, and it's always less than the theoretical yield because of human and instrument error. Now, you can calculate something called the percent yield of a reaction. It's a useful way to relate the actual yield to the theoretical yield, and it has the following equation. It's actual yield over theoretical yield multiplied by 100%. Okay, now let's put these two ideas together and tackle a practice problem. This problem says a student determined her yield of aspirin was 1.6 grams. Okay, so the student went in the lab, she made aspirin, she got 1.6 grams. Given that the salicylic acid in the reaction shown below, all right, what is her percent yield? You have 2 grams of salicylic acid to start off with, and there is a 1-to-1 ratio between salicylic acid and aspirin. Okay, so we're given this equation in an interesting way. We're given our mole-to-mole ratio, so we don't really have to worry about anything. And we're given how much grams of starting reagent we have. Okay, so here's the equation. We have salicylic acid reacts with acetic anhydride to give us aspirin and acetic acid. And what we're trying to figure out first and foremost is if we have 2 grams of this starting material, theoretically, how much aspirin can we make? That's our first objective. All right. And then when we have our theoretical yield, we can actually compare it to what the student actually made in lab, what her actual yield was. And then we can take the theoretical and the actual yield and calculate her percent yield. So to calculate the theoretical yield, we start off with 2 grams of salicylic acid. We're going to convert that to moles of salicylic acid using molar mass. We're given that 138 grams per mole of salicylic acid. What you notice here is grams of salicylic acid cancel out, and now we have units mole of salicylic acid. Next step is to use a mole-to-mole ratio to convert from salicylic acid to aspirin, because ultimately we want to get the theoretical yield of aspirin. And we were told that there is a 1-to-1 ratio between salicylic acid and aspirin. So that's our mole-to-mole ratio. 1 mole salicylic acid to 1 mole aspirin. These units cancel. Now we have moles of aspirin. And then last, we can convert moles of aspirin to grams of aspirin using molar mass. We're also given that 180 grams per mole. All right, and so our final answer is going to have units of grams of aspirin. Sorry, let me write that down, grams of aspirin. And if you calculate it, what you'll get is 2.61 grams of aspirin. That is our theoretical yield. Now, When the student actually went into lab and tried to make aspirin, she only made 1.6 grams. And so her actual yield is going to be 1.6 grams, her actual yield over the theoretical yield, which is 2.61 grams, multiplied by 100%. This gives us a percent yield of 61%. Wonderful. Let's do another example problem together. This is going to be our last example problem for this video. It says how many grams of solid iron can be formed if we have 50 grams of iron oxide that reacts with 10 grams of carbon monoxide. Okay, so we know we have 50 grams of iron oxide, 10 grams of carbon monoxide. So in a reaction stoichiometry problem, if you are given the mass of two reactants, you have to decide which is the limiting reagent. And one way to do this is to set up two cases, calculating the maximum amount of product you should get based off of each reactant. And the reactant which produces the least amount of product, that is your limiting reagent. And the other reagent is the excess reagent. So that's what we're going to do. We're going to start off first with 50 grams of iron oxide and see how much solid iron we can form. And then do the same thing with carbon monoxide and then compare those two values to see which one is less. That's our limiting reagent. Okay, starting off with iron oxide, we have 50 grams of iron oxide. We want to figure out grams of solid iron. So the first thing we want to do is convert this to moles of iron oxide. The molar mass for iron oxide is 159.7 grams of iron oxide for 1 mole of iron oxide. You can calculate this yourself as well, but I'm just going to give it to you for sake of time. Next up, now that we have moles of iron oxide, we can use a mole to mole ratio to convert this to moles of iron. This is a balanced equation. So for 1 mole of iron oxide, we have 2 moles of iron. So 1 mole of iron oxide, let me write that down properly. For one mole of iron oxide, we have 2 moles of iron. Okay, and now our last step is to convert moles of iron to mass of iron using molar mass. So the molar mass is 55.85 grams of iron for 1 mole of iron. All the units cancel out except grams of iron, and what we get if we calculate this is 35 grams of iron. Beautiful. Now we want to do the same exact thing, but with the carbon monoxide reagent. We have 10 grams of carbon monoxide. First thing we want to do is convert that to moles of carbon monoxide using molar mass. For 1 mole of carbon monoxide, we have 28 grams of carbon monoxide. Now we have moles of carbon monoxide. We can use mole to mole ratios to move from carbon monoxide to solid iron. For 3 moles of carbon monoxide, we have 2 moles of iron. So we're going to set that up. For 3 moles of CO, we have 2 moles of iron. And then again, we use molar mass for iron to convert it to grams. So 55.85 grams of iron gives us 1 mole of iron. And if you plug this into a calculator, you're going to get 13.3 grams of iron. Okay, so what we now know is that if all the iron oxide was used up, we could make 35 grams of iron. And if all the carbon monoxide reacts, we can make 13.3 grams of iron. Since using all the carbon monoxide results in the formation of only 13.3 grams of iron, which is less than the amount that can be formed from iron oxide, obviously CO is the limiting reagent, and 13.3 grams is the maximum yield of solid iron. And that's how we use, stoichiometry to figure out limiting and excess reagents. And with that, we've covered every topic that we wanted for this lecture. I really hope this was helpful. Let me know if you have any questions, comments, concerns down below. Other than that, good luck, happy studying, and have a beautiful, beautiful day.